Hi, today it's the 16th of May and it's 6 o'clock p.m. and I'm glad that my student joined me to his lecture. Today I planned to discuss, to learn, to teach about cycles with real gases, meaning the most important cycle of thermodynamics named Clausius-Rankine, the Rankine cycle. We will do a little bit of theory first. After that, I will show you what you have to complete in your first test. Be attentive that your camera is out. And do you hear me? Yes, okay.
Yes, yes, I can hear you.
And after that, we must try to start to make at least easy exercises, because thermodynamics means also a lot of exercises.
Okay.
Do you have any means to calculate? Do you have a computer?
Yes, yes, I
Yes,
have.
okay. And do you have a pencil and
Of course.
to to write? I propose. Okay, okay. So let's start first of all with the well-known. I don't know if you know this campus background. Do you know it?
Mm,
Do you see it?
yes, I can see it.
Yes, we are celebrating this year 100 years of existence.
Mhm.
That's why we are proud to have it. So let's start. Oh, so we will speak about the real substances, real gases, in particularly. We have up to now learned about transformation processes for ideal or for perfect gases. The ideal gases do not exist. They are a model. The perfect gases are gases that exist but have very many similarities to this model, especially when they have a low density. Low density means low pressure, high temperature, according to the equation of state. The real substance, the real gases, are totally different from perfect gases because they have some special possibilities to change the phase, to change from gas to liquid and from liquid back to gas. This is practically not taken into account for perfect gases. As the best example is the water with its vapors. Water vapors are formed from water. The water vapors can turn back to liquid, and the liquid can take a vaporization process and turn into vapors. With all these vapors, because the properties are totally different from the liquid, from where they are originated, a lot of tables of specific properties have been formed. And from these tables, the so-called state diagrams are resulted. We will need, at least to give you an impression, to analyze at the end also the tables I have sent you in Romanian, but at least you can mark on them when you go home a little bit of translation, and important is to know that they exist and to find the similar data in English. So important is to understand them, how you can use them, and only when you will need in an exercise or in your future job, you have to use data from English table or whatever it is used in your country.
Okay, understand.
So the gases are compressible substances. The liquids are not compressible substances. The I don't know the form in which a substance can appear is solid S, vapor V, liquid L. And there is a so-called triple point where all the three aggregation status are occurring at the same time. For an perfect or ideal gas, as you know, there are special laws that have been delivered, especially the main one is the equation of state. PV divided by T in Kelvin is constant. The representation in three dimensions in space, PVT, for an incompressible substance is like this, and for a compressed ideal gas, perfect gas, is as you see it.
Excuse me, but your screen is still on the first page you started with. Campus virtual and
Okay, I go back. Oh. Do you see it now?
Yes, now I can see it.
And now?
Yes.
Okay, this is a little bit complicated, but we will work further on with these diagrams that are not in space, but only two-dimensional. So, what you have to understand is the following. Let's say we have ice. Let's make an experiment. We have a piece of ice of minus 20 degrees at normal pressure. Outside is normal pressure. What is a normal pressure?
It's 1 atmosphere.
One physical atmosphere. You must stress physical, because the technical atmosphere is something less. And we are warming this piece of ice. What do you suppose it will happen? We are warming it up. The temperature of the ice will
increase, of course.
Will increase up to
is it safe? I don't know. I don't
up
see.
to 0 degrees Celsius. When it starts to
start to be
melt,
liquid.
melt, yes, and to turn into water, into a liquid, yes. At this point, we must continue to warm up, to put energy into the system. But despite this energy input, the temperature of the water still remains the same. The temperature of the water and ice mixture would be more correct, because the ice doesn't melt in a second, in instant. It melts in time, and during this time, ice and water are together. Ice is at the surface because it is lighter than water, and you can see both phase. You can see a mixture, yes? Now, the question is, what is the temperature of the ice and what is the temperature of the water?
They should be equal.
They are equal and both 0 degrees Celsius. Finally, we reached to melt all the ice and continue to put heat into the system. What happens?
Until it gets 100, it starts boiling.
So first it warms up 20, 30, 50, 90, 99, and suddenly it starts boiling, and you see the first vapor is coming out, yes? And this vapor is meant saturated vapor. It has the same temperature as the water from which it is formed, but up until the not until the water still exists and is not completely turned into water, both water and vapor have the same temperature, that is how much?
100.
100 degrees Celsius, very correct. So you see that at 100 degree, according to the normal pressure, you can have two phases in equilibrium. They have the same temperature, so they are in equilibrium. The vapor and the liquid are forming a mixture, and this mixture is characterized of a special rate between the mass of the vapors and the mass of the mixture, and this is named X. Yes? The quality of the mixture is indicated by this rate. The temperature for the vapors and for the liquid is the same, but the liquid has totally other properties, uh, total different from those of the gas. And that's why tables have been made that are indicating at special pressure what is the temperature of saturation, of vaporization, and what are the properties separately for the liquid and separately for the gas. Those for the gas, for example, volume, specific energy, enthalpy, entropy, are all having G from gas. And those for liquid have L. And according to the value of X, the resulted properties for the mixture, meaning the specific volume of the mixture, the specific internal energy of the mixture, the specific enthalpy of the mixture. In Romanian, we are naming it with I, yes? And the specific entropy, they are having X, yes, X, and they are formed by summing two factors. One, X, the specific property for gas, plus 1 minus X, and the respective property for the liquid. And all these values are taken from tables. So very clever persons made with all these values diagrams. And sometimes these diagrams are more useful because they give you a lot of information, even despite the fact that if they are not so large, you can read not so exactly the points as you read them from the tables. But normally the tables are very, very compressive. They are like a Bible, so thick, very thick, yes? Or like a Quran by you, yes? The books are very, very so let's have in mind such a diagram: temperature, entropy. The values are in BTU. It was the only diagram I found in English. So I will explain you with this diagram, yes? This is exactly what happens with the example when we what we made with the ice. The ice is warming up, The ice is melting, turning into liquid. The liquid is warming up and finally turns into vapors. What I showed you here, it is a process that occurs at constant pressure. Here is the pressure a lot, but in our example, it was a normal pressure. So for each pressure, the phenomena is the same, but the values are different. Yes? You understand that, yes?
Yes.
Okay. So, as you see in a TS diagram, that is very much used in such, it is named temperature entropy diagram, the temperature entropy diagram. You can see this mountain, this curve, yes? The right part of it is designated to saturated vapors. The inside is designated for the liquid and vapor together, forming a mixture. And the left side is dedicated to the, what is left? The liquid.
Triple point.
No, we don't have here a triple point, yes, in this diagram. The triple point is for water here somewhere, yes? But at this moment, we are concentrating here on this critical curve. So if we want to indicate temperature, the temperature is an horizontal. A vertical means entropy constant. Mm-hmm. So please take a pencil and make a diagram, temperature, entropy, and design only this mountain.
Okay. The temperature is in Kelvin or Celsius? Okay.
Okay, then start from, let's say, take a temperature T1 and start construct with me. Look at my pointer, yes?
Yes, I can see.
Start, for example, here and and make a line up to here, like this, yes?
Okay.
Then make a horizontal and then approximately a vertical.
Okay.
This is a process that normally can appear. We will design now isochoric pressure constant. The pressure constant is
Pressure constant isn't in isobaric.
isochoric, yes. Let's take a point, for example, here. Constructed a curve up to here.
The same line as before, or
So from this side here, then horizontal, and then a little bit vertical, yes? So this is a isochoric process for a real gas. As you see, this horizontal part in the interior of this specific curve represents the two phase liquid and vapor in equilibrium. The pressure, the isobaric process is also isothermal, P and T. During this specific moments, yes? So this curve delimitates to the right state of gas, vapors. In interior, we have two phases, liquid and gas. And in the left, we have a liquid region. So what you can see that if you work at a higher pressure, the isobaric process has the same aspect. For example, like this, as I show you. Okay, but what you see, the horizontal part is less and
yes.
less, and in one point, at one moment it is turned into one point. This means that the transformation from liquid to gas happens in a second, instantaneously. Here you had the possibility to have two phase joining. Yes, but here you turn the liquid instantaneously into vapor. And this pressure is named critical pressure. And this point here, top of the mountain, is named critical temperature. This is a critical point. So now we have a limitation also here in this superior part. Yes, by the critical pressure isobar. So here you can see what I told you. It is an exaggerated diagram to show the liquid. This is the liquid region, this is the gas region, and this is the two-phase region. Yes?
Yes.
So everything that is here under this curve, all these points are representing water and vapor at equilibrium, at the same temperature that is named saturated temperature, and that is in a direct connection to the pressure at which we are doing the process. The higher the pressure, the higher the temperature is. If we have here a point, let's take this point, yes? We can say that from the tables that I mentioned, we will take out values for the liquid here and for the vapors here. And in order to characterize this mixture, we will use these formulas with X. Is it clear? The X constant are curves that are coming down like this. They can be treated as similar to the saturated vapors.
Okay.
So let's resume. A constant pressure heating process for a real gas gives us the opportunity to turn liquid into a mixture liquid with vapors at saturation, and further to turn the vapors into superheated vapors that have a temperature higher than the saturated vapors. So the superheated vapors have a higher temperature than the saturated temperature.
Okay.
For the superheated vapors, we have other tables and other diagrams. So most of all of these problems are solved with the means of tables and diagrams. You have to know that there is another specific Molière diagram, enthalpy entropy. As we don't use it so much here in Romania, I am only show it to you in order to have an idea that it exists. Yes?
Yes, yes, I.
So the TV diagram for vapors is another diagram that is used. So you have to learn specific expression. Liquid, subcooled liquid, vapors that are wet when they are in mixture with liquid, and superheated vapors. Gases that are in a special region, here it is, they cannot turn into liquid anymore. Here are two diagrams, the PV diagram and the TS diagram. The TS diagram is used in order to understand the phenomenon. The PV diagram has been used to construct all the tables. So I will insist again about the TS diagram. Here you see the curve with both its branches. Here the right side is x equal to 1, the left side x equal to 0. And here is the critical point. So let's take water, liquid, warming up, vaporization. All this, this horizontal means that at the same temperature, liquid and vapors, liquid and vapors are sharing the same temperature and form a mixture in equilibrium. Here in the left point, we have only water, water at saturated temperature, and here in the right point, G represents
only gas.
Only gas, saturated gas. And heating up means to obtain, heating up at constant pressure to obtain superheated vapors, gas. Yes? And this phenomena is occurring up to a special pressure named critical pressure, when this horizontal part of the isobaric
Process?
Isobaric representation is disappearing and is resuming to an only point named critical point. From this critical point, you have, as this line, constant quality lines, meaning x is equal to, is constant. Yes?
Okay.
So we resume. What you have to know, here is a zone with subcooled liquid. Here is liquid at equilibrium. Here you have wet vapors, meaning a mixture between liquid and gas. Here you have saturated liquid, saturated vapors, and here you have what? Superheated gas. Yes?
Okay.
So we will learn about the vapor power cycles, meaning the Clausius-Rankine cycle, that is a theoretical but conventional steam generator cycle. Or the main cycle for the steam power plants. You have to understand combustion technologies. You have to know how a steam generator works, how a turbine for water, for vapors works, and finally, what a combined or cogeneration power cycle means. So from the Carnot cycle, you know that it is the most efficient cycle. It is an ideal cycle that doesn't exist, and the efficiency is calculated always for a given cycle as 1 minus the ratio between the minimum and maximum temperature in the cycle expressed in Kelvin. The Carnot cycle is mentioned to be formed by two isothermal and two adiabatic reversible processes. So Rankine wanted to construct a real cycle that is as much as possible resembling to Carnot. So he used also two adiabatic reversible processes, and instead of the two isothermals, he used two isobaric processes, because as I told you and you understood, most of the isobaric process, so or at least a part of the isobaric process, is also isothermal. So the resemblance to the Carnot cycle is at least very close. Is it clear up to now?
Yes.
Okay. So here is again the efficiency is given by 1 minus the ratio between the heat and cold reservoir. The Carnot cycle in a TS diagram is A, B, C, D, as you see it. A, B, a vertical. It is adiabatic warming up process, heating process. BC horizontal is an isothermal expansion. CD is a compression, but adiabatic compression. And DA is an isothermal compression, isothermal, DA, yes? So as you know, from the second law of thermodynamics, it is impossible for a cycle to run a motor cycle if it is not in connection with at least two reservoirs. So from the surrounding, the system receives at TA, high temperature, energy input in form of heat. He at the cold reservoir receives from the system another part of heat that cannot be used by the system, unfortunately. And in the meantime, the system is doing some work for the surroundings. Here is the expression of the thermal efficiency. Oh. So the Carnot cycle can be imagined also for steam. Here is the TS diagram with the Carnot cycle, but the steam used into the cycle in this example is not superheated. It remains, C is the point of this curve. It is saturated vapor. We don't have superheated vapor in this example. Yes? So A is a mixture of water and vapor at the temperature TR, the cold one. B is only what?
Liquid.
Liquid at the temperature of the high
A,
temperature.
high temperature.
C is saturated vapor at the same temperature as B, yes?
Yes.
And D is at the same temperature as A, but it is what? A mixture
Of
between
liquid and
liquid
gas.
and gas, but in a different amount as A.
Yes.
Yes? Here we have, this is liquid and this is vapor, and here this part is liquid and this part is gas. This Carnot cycle in TS diagram can be put also translated in a PV diagram. It is the same. Here we have the representation, even these two are not horizontal. They are a little bit, you must think C is not at the same level with B. It is a little bit higher. And D and A is a little bit higher than D. These are not horizontal because this is a PV diagram, not a TV diagram.
It's not D that higher than A?
I beg your pardon? Okay.
Is it supposed to be B higher than A?
Okay, I will make here, I don't know if I will can. Oh. Where is a green shade fill? Okay. Okay, so, so this blue, this green is you must cut it, yes?
Okay.
It's not P, it's T, yes? T. So, and here you have the steam power plant comprising a boiler, a turbine, a condenser, and a pump. 4 things, yes?
Yes.
The boiler is responsible to receive from the combustion the heat and turns the energy of the fuel into energy of water that is turned into vapors. Yes, here. The vapors are entering the turbine and are giving their energy to the turbine. This is a detention, CD, this vertical. Adiabatic process. And the turbine transforms the energy received from the vapors into mechanical energy that goes out. And normally it puts into motion the electric generator. And that's why the first result of the cycle is electric energy. So we start here with an input of fuel energy, and the output is electrical energy. Electrical energy that everybody wants to have it, yes?
Yes.
From the turbines, the gases come out in a less activated status because D is under C, less temperature, TR, the cold temperature, and it is represented mainly by a mixture of vapors and water. And in order to reuse this mixture, to put it into the pump, you have to turn the mixture into more liquid because the pump can't work with gases. The pump normally uses liquids to work. And from A to B is the work of the pump. You have to put work into the pump. The process of condensating, of turning from D to A is happening in the so-called condenser. In the condenser, the temperature is constant. And this occurs by taking out from the condenser of this heat. This heat in the TS diagram is represented by this area that I indicate you. So as second result from this cycle, we have also heat. This heat can be used or can not be used or is not used. Yes, it always could be used, but it is not always used.
Yes.
So if you use both, you speak about a cogeneration plant, meaning from one source you produce two energies. One is electric energy and the other is heat energy. This is the best situation.
Can you make it bigger so I can focus more? Yes.
But as you know, I uploaded you also the last course in YouTube, and you have the registration in your campus.
Yes.
Have you seen it?
I searched for the second lecture, but I didn't find in the campus. It's only the first one.
I have to look.
Maybe I can find it. If it's the same channel, I can look it for on YouTube.
Yes, it must be the same channel.
Yes.
So the Rankine cycle is running with water. So we have A, water, B, water, but A is a low pressure water. When it enters the pump, here is A, here is the same A, yes?
Mm-hmm.
B, when the water enters the boiler, the water is heated, then it is turned into vapors. So D is going into the turbine, the exhaust is E. So this A, B, C, D, E is a Rankine cycle with saturated vapors. Is it clear?
Yes.
You have to put into the system heat with the fuel and energy for the pump, and you take out at least mechanical energy that is turned into electrical energy, and if it is possible, also heat from the condenser.
Mm-hmm.
So this Rankine cycle is formed by two adiabatic processes, DA detention, ABC compression, and two isobarics that are at the same time are also isothermal processes. Yes?
Yes.
And this is a power plant in, let's say, another view. So into the boiler, you put air and fuel. I have sent you an open source for the Rankine cycle. Have you seen it?
The last PDF, yes.
It's
The
not,
last Word file, yes.
yes, it is not, it is a very nice picture, a very nice film in YouTube. So with animation.
Okay, I'll.
You must follow it because it is very interesting. Even it is an animation, but what the guy is saying, you will for sure understand it and love it because it is nice, very nice. So this is a steam generator. From the steam generator, the flue gases are going out. But the steam is going into the turbine. The turbine has on its shaft electric generator. The exhaust of the turbine is formed of a mixture of liquid and gas, and is going into a condenser where the cooling water takes out the heat from 2 to 3, enabling the mixture to turn into liquid. And when 3 is only liquid that is entering to the pump is pumping the water back to the steam generator. So we have here in the turbine the isentropic expansion. The inlet 1 is saturated vapors. The heating process of the water in the generator is 4 up to 1. the process in the condenser, and it is an isobaric process, partially here also isothermal. And from 2 to 3, we have what?
We are
The condenser, yes, that is taking out the heat from 2 to 3. This in TS diagram, every area represents heat. So this squared form is the heat that is going out from the cycle. Oh, there are practical limitations because in theory we have one, and in reality no adiabatic process can occur. So normally the detention in the turbine is a vertical, but in reality entropy is going up, so the real point is not 2s but this 2 that is a little bit shifted to the right. And 3 4 is not a perfect vertical. 4 in reality is a little bit to the right of this 4 mentioned here, because always the adiabatic processes cannot occur in reality. They are reversible, they are irreversible, and the entropy is always going up. The difference between this situation and the situation in the other, in the previous slide, is that here we have a superheater. The superheater is doing this part. His job is to turn the saturated vapors into superheated vapors. Thus, the steam generator works from 4 up to 1. 4 is water and 1 is superheated vapor. But they both are all on the same pressure. So the high pressure isobaric process is 4 to 1, and the reduced pressure isobaric pressure is 2 3. The adiabatic processes are 3 4 and 1 2. Have you understood what the superheated heater is doing?
I'm not sure actually.
So what is the difference in the previous? You had the one on
Yes.
the curve, yes?
The one here is vapor, but there is superheated.
Here one is not superheated. Here
Yes.
one is at saturation, yes? And now
It's superheated here.
it's
At the second.
superheated, yes? This is the difference, yes? And for that, you need a special part in the steam generator to superheat it, to do this job. Here, this one. Yes? So the thermal efficiency is the ratio between the net work transferred in the cycle to the heat supplied that is positive, and the network is also positive. So here is an example. You can have this example, and perhaps you can use also the values. I go back here to this situation here. In the reality, the detention from 1 to 2 is, as you see, with entropy increase, meaning point 2 is more right than point 2s. And this is a benefit for the turbine because in its last part, it has less liquid droplets actioning on its pellets. And this means a less erosion by these droplets. Is it clear? So it is a benefit for the turbine because the turbine is put into movement by the energy of the vapors, yes? At the beginning, they are only vapors, but up to here, they start to be mixed with water. And this water, they how to say, generate a mechanical erosion on the blades. And the less liquid you have, it is much better. So the situation 2 is for the turbine better. You have to remember this. So we intend to improve the cycle, the Rankine cycle. And for this, we will use 2 turbines, the high pressure and the low pressure turbines. This means that normally 5, 6 the pump, 5, 6 the pump. So 6 is the point water goes into the steam generator. The steam generator warms up the water, turns it into vapors, and then into superheated vapors with this superheated number 1. Yes? Then the vapors go into the first turbine, the high pressure turbine, and expand, give their energy to the turbine, and with the characteristic 2, go back to the steam generator in the second superheated or reheater section R, yes? And the process from 2 to 3 occurs. And after that, the second turbine that is much more larger is doing the process, theoretically, the vertical from 3 to 4. What do you see? That you have this vertical, you have now 2 verticals instead of only 1.
Yes, it's in order to get less liquid in it.
Not only, but you can obtain more mechanical energy, more electrical energy. Yes, what do you have to do is to build a reheater section, a second superheater, to do the job from 2 to 3. Yes? So this is a very useful modality to improve the efficiency of the cycle. But the best modality is to use district heating, meaning the cycle works in cogeneration. District heating, what does it mean? I don't know in your country if you have district heating. So meaning that homes are warmed up during winter from district heating system offered by the city hall or by a company. Do you have district heating in your country? No, because it's very...
No, we don't use it.
You don't use it. So
yes, exactly.
But here in Romania or in Europe, or if you go in Scandinavian countries, they all use district heating at least during winter.
Yes, I can see.
But you can use this heat not only for district heating, you can use it also for, let's say, a factory that needs heat. For example, a factory where you have to paint something or you have to wash something. You need hot water, yes? Or you have to wash some bottles to put I don't know what food inside, or sterilized cans and so on. So to use the energy from 4 to 5 is the best modality to raise the efficiency of the cycle. The first possibility is district heating, but you can use it also in another factory that needs heat. Yes? So here you have a much more sophisticated situation, the blade extraction for regenerative heating. So this is another modality to raise the efficiency. So up to here you understand, this is a steam generator with the first superheated, the first turbine, the high pressure turbine, the reheater, and it goes back to the
second turbine.
Second turbine, the process from 3 to 5. But some steam that has a characteristic of 4, yes, is taking out from by extraction from a blade. This is a blade, yes, and heat vapors are extracted and go into the feed heater, and this feed heater allows the I have a mosquito. Allows the water coming out from the pump to be heated from 10 directly to 9, let's say, and avoid all the previous work from 10 to 6 to 7 to 9. You understand?
As I see that it's 9 to 10, not 10 to 9.
7, 8, 7, 8. Normally it was 6 to 7, yes, and further to 8. But now the and this and 6 to 7 to 8 was done by the steam generator. But now if you use this feed heater, the mixture goes directly into the pump and is warmed up in this heater, not in the
Generator.
steam generator. So you use your own heat to preheat the water to prepare it much better for a vaporization process. 9 is much more near to this horizontal as 7. You need
Yes.
here less energy. And if you need less energy to produce the vapors, this means you have a gain and the efficiency goes up. In a power plant, if you raise the efficiency by 0.1, it is already excellent, yes, or 0.2. More you cannot obtain. So in conclusion, the thermal efficiency can be obtained by making the ratio between the energy used to the energy resulted to the energy used, the energy input. So energy output to the energy input. The energy output can be the electric energy expressed by mechanical energy and or standing alone. The energy offered by the condenser. 2, the input energy, that is the energy of the fuel through combustion. So the higher the superheated parameters are and the lower the parameter in the condenser are, you manage to get a higher efficiency. Think at least at the Carnot cycle that has an efficiency depending on only on the higher and lower temperature. 1 minus T min to T maximum. So if T min is lowered and T maximum is higher and higher, you can obtain a higher efficiency. And this is also very correct for the Rankine cycle. So you can use the district heating or at least cogeneration by using the heat from the condenser. You can use regenerative heating of the feeded water, the last situation. You can use several turbines and intermediary heating in the superheaters and several expansions. So you can have at least 3 turbines, high, middle, and low pressure turbines. And you can make combination of all those. Normally, combination of all those are running in reality. The efficiency can also optimized by an improved mechanical efficiency because the turbine shaft is acting on the electric generator. And if this mechanical efficiency is not very good, you get here some losses at least. Yeah. The combustion must be also very well controlled. So you have also, you must have a good efficiency in the boiler. And also the electric generator must work with the improved electrical efficiency. So from a power plant, normally you need the electricity output as energy form based on the heat input with the fuel. And in special cases, you can use also the heat resulted from the condenser for district heating or for other industrial purposes. Yes, in a company. So that's all. The second I will introduce you what I will upload you in the it was a question. I will upload you this file in the campus as well. So the overpressure is the sum between the barometric pressure and the overpressure is the calculation pressure is the sum between the overpressure PS and the barometric pressure. So PA is PB plus PS. PS is the overpressure. And in case of a depression, the PA is PB minus the depression. All these are, how to say, like this. Huh? So perhaps it's better, yes?
Yes.
Okay, you will find here some nice information about atmospheric pressure. You have to read this small lecture I prepared specially for you, yes? So I presented different types of pressures, yes? Overpressure, depression, absolute pressure. You calculate always with absolute pressure, always. Also, you learned about the Bernoulli law, that the dynamic pressure is the difference between the total pressure and the static pressure. And the dynamic pressure is always expressed proportionally to the velocity, square velocity. And here,
W is velocity.
yes, W is velocity. And here I gave you a table of what are several device types of equipment that are measuring the pressure. So you will get this file in your folder. And remember these expression, but very important is that you are calculating always with the absolute pressure, PA.
Pressure.
Yes?
Okay.
The normal pressure is this. The barometric pressure, you have to measure it, how much it is. It can be normal, but it is not always normal. Yes? Okay. Now we will take your pencil and we will do some exercises by representing different transformation. So design PV diagram and make a vertical. What does this vertical mean?
Constant volume.
Constant volume. If you put a point 1 here and 2 here, which one has a larger pressure?
1.
1. So you can say that 1, 2 is a, how to say to this? Isotonic
process.
detention. Yes, detention means that the pressure goes down.
Okay.
Yes, it is the opposite of compression. So if you put a point 1 here and 2 above, it is a
Compression.
isochoric compression. Yes? Let's take the TS diagram and we should represent the isochoric processes in the TS diagram. They are like this. Yes? So let's say this is an isochoric V1. Let's say this is V1. If you take a V2 to the left, means higher.
Okay.
In the TS diagram, the curve goes this direction. So it will be like this. You have to design it. So the V goes up in this direction in the TS diagram, and in the PV diagram goes to the right. So here it goes, let's say, also to the right. Yes?
Completely the right, or as it is, like rotational?
You have like this, and here is another, let's say at least parallel to this. So let's take in PV horizontal. This is what? The horizontal.
Isobaric.
Isobaric, yes?
Isobaric, yeah.
This is, if you put 1 here and 2 here, you have a what?
Compression?
No.
It's constant pressure.
Constant pressure, but the volume
is larger.
Is larger. That means the tension, yes? Expansion. Yes? And vice versa, if one is here, the start point, and the finish point is to the left, you have a
less volume.
Less volume, so a
I don't know the name.
Isobaric compression. So compression means not only the pressure goes up, it can mean also the volume goes down.
Okay.
For the same meaning, yes?
Okay.
So let's take the TS diagram. Here is a isobaric process, yes? Let's say this is P1. And if you take a P2 higher, here is higher, the curve will move to the left, like this.
Okay.
Yes?
Yes.
Okay. So let's take the isothermal. T is constant. T is constant is a hyperbole, like this. Yes? And in the TS diagram, it is a horizontal. In the PV diagram, the bigger T is, the curves goes to the right, like this. Yes? And here in the TS diagram, the bigger the T is,
Goes up.
it goes up. Yes? The adiabatic process is also a hyperbole, but not equilateral. It is a curve like you see it. It is more vertical through the same point.
Yes.
As a isothermal. And in this diagram, it is a vertical in the TS. Yes? All other curves in PV are possible, and they have a correspondent in the TS diagram. So this is very important, and if you understood this, you will we will see in a special essay. So first of all, you have to complete your first essay with the remarks I gave you in the campus. Let's see what I wrote to you. As I remember,
Okay.
so essay number 1, okay, you send it, and here is your submission, and if you go to see it, the feedback is the following: complete exercise 1. Let's see it. Exercise, no, not 1. 1 is okay. Here, 2. Vacuum barometric pressure. Complete exercise 2. Now I showed you how you must make this sketch and these formulas that I gave you today.
Okay.
Yes. Here perhaps a little bit more, but it's quite okay. Here it's okay.
I don't think so.
The exercise 5 must be completed. You wrote me only the law of Dalton and nothing more. Look at the lesson with mixture. The lesson with the mixture. Where is it? I don't know if it's here. No, it's not here. We have a lecture with a mixture. Second, first, here. The mixture, yes? You have to put all these formulas and understand them.
Okay.
So, exercise 5. This is okay. This is, let's say, quite okay. The volume is not in liter. The volume is in squared meter. Correct here.
Okay.
Here at 8, you have to complete exercise 8 with all the drawings we did now. Yes?
Oh,
Because now you understood them.
okay. The problem is it's hard to do the.
You can do it by hand and make a picture with your phone. Yes?
Okay.
And named it picture 1, picture 2, picture 3, and put them all together and make a PDF with all.
Okay.
Or separately, or as you wish. Yes?
I can add it with the same.
You
file.
can edit, yes?
Mhm.
Or you can make a picture and put it directly where it must be. Yes?
Okay.
And here the PV and TS diagrams, you must complete it. Because now you understood. Here you put nothing. I don't know.
I didn't know what to put.
Okay, now you know what to put. You take this out, yes, and you put what I learned you. Yes?
Oh, okay.
You have to put the last drawings. Yes? So save changes. I send it back because I want to give you a good grade. Yes?
Okay.
I will open the no. So here it is, the essay edit settings. I will open it. Due date, how much? Is it sufficient 1 day or 2 days?
As you like. 2 days maybe.
2 days. So today 16, 17. I put 18 here. It's okay for you? 18?
Okay.
18 is Monday. Yes?
Mm-hmm.
It's okay for you, yes?
Yes.
Okay. Save. When you send, you say corrected file
Okay.
in order to have to see that it is a new file or something like that. Yes.
Okay, okay.
Okay, here open source information in thermal energy. Have a look to this. This is very good, very good. Copy. Now you don't hear too much. You don't hear it, but you will see it. Oh no.
Basic concepts of thermodynamics.
Okay.
At the end of this lesson, you will be able to define thermodynamics.
So you have to hear. This is the Rankine cycle, and where is the you can you have a look. Yes, what do you like? You can use it.
Okay.
Let's see. I have another one very good. Okay, let's see. Copy. This one. Oh no, it's the same. It's the same. I can't find it now. Okay. Here. You see, here is a power plant. You see the picture. This is a power plant. This is a boiler. You see it?
Yes, I can see it.
This is a boiler. These are the two turbines. This is the electric generator. The flue gases are going out. This is a filter for the particles. Desulfurization, denox, and the flue gases go out, cleaned up. You see? And this is the inlet of the boiler is like this. It is full with heat exchangers. Here you have the superheaters. Here is the air preheater, the water preheater. Here is the system where the water turns into vapors. Here you see the turbines, the generator. You like it? And here is another sketch for, this is the boiler, the turbine, the electric generator, the condenser, the pump, and this is the cycle. Yes?
I can see.
And here is the inside of a large boiler.
Oh.
Oh, this is the furnace. These are the two superheaters, three superheaters. This is with blue the air superheater, with red the water superheater or economizer. And here, oh, this one, copy. I think this is, on my opinion, the best. Oh no. Oh. Here, the thermal power plant. Hmm?
Okay.
So, look at the. Do you hear something? Yes?
Actually, no.
Do you hear something?
No.
Hello?
Yes, I'm with you, but I can't hear the video.
Okay, so copy. Do you see something?
Yes.
Uh-huh. Okay, I think this is a turbine. Do you see? It's interesting, yes?
Mm-hmm.
Okay, then you will make it by yourself, yes? I
Okay.
stop it. And let's write here the Rankine cycle. Oh. Oh. So this is the best. Best. Yes? Oh. Okay, then I think we can close the lecture today. I think you learned a lot. What is your impression?
Good.
Good, you learned a lot. I hope you understood. And we will meet when? I think Monday. Yes.
Yeah. You didn't
Monday.
give me the next.
Monday, Friday. Monday and Friday, yes?
Okay, but you didn't send me the.
No, I didn't, because I wanted to ask you. You have to look into the assignments. You have
The
to
compass or the email?
look the campus.
The compass there is nothing. I don't know why.
Okay, I will show you where you have to look. Here in the announcements, yes?
Uh-huh.
Yes, you have here all the Zoom lessons.
Oh.
Yes?
Yes, okay.
Yes, and you might click on it and you see when it starts, not when I posted them. Yes?
The last one is today.
The
There
last
isn't.
one is today. Yes, this one.
Yeah.
Yesterday was this. Yes? It's okay now.
Yes, yes.
I will add the new topic and put you the new invitation.
Okay.
Okay, yes? So, it passed already 2 hours, very much. So we will have an end. Have a nice weekend. You must work hard because you have to learn in several weeks what you didn't learn in several months. Yes? So bye-bye and see you next time.
Thank you.